Hello everyone, so welcome back again to my channel. So last time we have talked about entanglement distribution, entanglement distribution in between distant two parties. So currently I am working, as you know, I'm doing my PhD at Okinawa Institute of Science and Technology in Japan. So my focus is like I usually work on quantum information, quantum computing, quantum communication, all these type of things. As this is my out of field lab rotation, so I'm working in machine learning unit, and the project is quite interesting. So today we are going to talk about that. Um, and so the project is about the optimal transport. uh, so let me give you a simple idea in layman language. You can see you can say suppose a construction work is going on around near to your home. Like the sands, so for the construction work, we need sands, bricks, all these type of things, right? So for example, let's say we need sand. So we have to transport that sand to the constructive, like where the construction is going on, to that place. So the optimal transport chooses the minimal cost, which requires from moving one mass to the another place. In mathematical language, it says optimal transport chooses the minimal cost between initial distribution to final distribution. So this is the today's topic about. So I'll tell more about these things in a moment. So let me share my screen. Okay, so I'm sharing my screen. Let us share. Yeah, I think I have shared my screen. I hope my screen is visible to you. I think so. Okay, let me make it full screen. Okay, so uh, 1 second, it's not working. Well, let's see. Yeah, yeah, I hope the screen is visible to you. And yeah, so I just wanted to make this person like, yeah, now it's fine. That's nice. Yeah, so as you can see, our today's topic is optimal transport matrices for battery charging cost estimation. So my lab rotation supervisor is Professor Makoto Yamada, which I'm working in machine learning unit. So let me introduce the contents. So first we'll introduce the optimal transport problem, then we'll go through Mond's problem, then controversy relaxation, then different type of distances like versus time distance, slice versus time distance, and generalized versus time distance. Then we have shown applications of optimal transport in charging of batteries. So we have considered two examples, like one-dimensional battery model and two three-dimensional battery model. Then I will show some results and will conclude the presentation. So the first question is like, what is optimal transport? So the optimal transport finds the minimal cost way to transform one distribution into another by moving mass as efficiently as possible. So as you can see in the animation, like the left file is the initial distribution and the right file is the target distribution. There are many ways to move the mass, right? And the optimal transport chooses the like the transport plan that minimizes the total work. Okay, so next I am going to talk about the first optimal transport problem, which was like introduced by Mons in 1781. And the key idea is very simple, like it finds the single best mapping that moves mass from the source distribution to the target distribution. So the formula is given here, and but as we can see here, the idea is like the whole mass is transported from one place to another. So there are several limitations, which are like it requires one-to-one transport. Then it cannot split mass between multiple destinations. Um, Often no feasible solution exists for real world problems. Next, we are going to see the solution of this limitation, that is contribution relaxation. The idea is very simple, like so here Counterby is introduced that as you can see in the animation, the mass can be splitted and distributed, which makes the optimal transport convex and computationally tractable. The Counterby's relaxation is quite important because it always admits a solution. It handles complex distributions naturally. Also, it forms the mathematical formulation of Wasserstein distance and modern optimal transport. Next I am going to talk about like how it relates with the Wasserstein distance. So Wasserstein distance is a measure. Wasserstein distance is also known as earth movers distance, which measures the minimum amount of work required to transform one probability distribution into another. So for two probability distribution, the Wasserstein distance is defined here, and here as you can see, this carries the concept of mass splitting and mass distribution. Next, we are going to talk about another type of distance, which is slice Wasserstein distance. Here the idea is like to compute the full Wasserstein distance in higher dimensional space is computationally very expensive, because it requires solving a large optimal transport problems. So the smart idea is like instead of solving these difficult high dimensional problems, so we do like a linear projection in distribution onto many one dimensional distributions. Then we compute one dimensional versus time distance for each projection and average the results. So the formula for slice versus time distance is given here, and as you can see, the p theta of x is the linear projection onto direction theta, and wp is the versus time distance. So so to give an intuition about like how this slice versus time distance works, you can imagine observing a three-dimensional object from many different viewing angles. For each view gives one-dimensional projection of the object, and instead of solving transport in the full three-dimensional space, we solve many simple one-dimensional transport problems and combine their results, which reduces the competition. So next I'm going to talk about the last one, that is generalized slice versus time distance. And as we have discussed earlier, that the slice versus time distance does the projection linearly. However, in some real life problems, we need nonlinear projection. So to give an intuition, like imagine a particle moving on a curved surface. A straight line projection cannot fully capture their true geometry, right? So instead of that, so instead of linear projection, we replace the linear projection with a non-linear projection, which better follows the intrinsic geometry of the data. So for two probability distribution mu and nu, we define the generalized slice versus time distance formula is defined here. Here the formula is same as earlier, but here just instead of the linear projection p, we have used g naught of x, which is the non-linear projection. For example, like here you can take polynomial kind of functions. So in the next slide, I'm going to talk about like how we can use optimal transport in charging of batteries. So the idea is very simple. Like when we charge a battery, so the ion inside the battery move from cathode to anode because those ions got excited, and so in this case, like during the charging, the battery evolves from initial distribution to the charge distribution. So and as we know, optimal transport measures the minimum transport cost required to transform one distribution into the other, right? So the battery charging can be viewed as transporting one probability distribution into another. So if the transport cost closely matches the physical charging energy, which means the corresponding optimal transport metric becomes an effective estimator of battery charging cost. Next, we are going to talk about so here we have considered two toy models. like one is one-dimensional battery model and another is three-dimensional battery model. So next we are going to talk about one-dimensional battery model. So yeah, you can see here for this one-dimensional battery model, our parameter is only energy, and the state of charge is, as this is a toy model, so as the state of charge distribution is defined as the beta distribution, and it's defined as S naught, and the battery's charge state is defined as S1, which is greater than S naught. And as I mentioned that it's a toy model, so we can estimate the actual energy cost to charge the battery. So the function is defined here, and L is the noise, like some kind of heat or something like that. So we have taken here in the simulation, I have taken Gaussian noise. In the next slide, I am going to show you the results. So here we have plotted, as you can see, we have plotted in the x-axis, we have plotted the actual charging cost, energy cost, and in the y-axis we have plotted the predicted one by the metrics, like Wasserstein distance, slice Wasserstein distance, and generalized slice Wasserstein distance. The idea is like, as we are taking W actual divided over the W predicted. So if the slope is 1, so that means that the dotted line presents the actual one. Like if those two are equal, so it will give a straight line, right? And the slope should be 1. So so if it gives a straight line, that means our model works so nicely. And as you can see, also logically, if you think intuitively, like for one-dimensional problem, the Wasserstein distance works so nicely, right? So that's why, as you can see, the plot of Wasserstein distance is the best one. And the other argument is like the slice Wasserstein and the generalized slice Wasserstein doesn't work. They don't work because here the linear projection and non-linear projection does not give any further more information. So next we are going to talk about three-dimensional battery example, and before that you can see the performance data here. So for a three-dimensional battery example, here we have considered three parameters, which is energy, entropy, and temperature. So these variables together describe the battery's thermodynamic state during charging. The charged state is generated using an affine transformation, which is given here, and here the A is the coupling matrix, which is energy, entropy, temperature interactions, and B is the charge induced shift, and eta is random noise. Here also it's a toy model, so we know the actual charging energy cost, and the function is given here. In the next slide, I'm going to show, and here you can see we have plotted the same, like in the x-axis we have plotted W, like the actual energy cost, and in the y-axis we have plotted the predicted energy cost. And if you remember, like in the previous slide, the battery dynamics are predominantly linear in the energy in the energy coordinate. So the intuition is like the slice versus time distance should work so nicely. And as you can see here, the slice versus time distance is the overall performance of the slice versus time distance is better than the other two. So in the next slide, I am going to conclude this presentation. So in conclusion, the optimal transport calculates the minimum mathematical work required to transform one probability distribution into another. Also, this framework has vital application in image analysis, machine learning, and also we have seen in battery charging cost estimation, etc. So the key metric used to estimate this transport cost include versus time distance, slice versus time distance, and generalized slice versus time distance. For one-dimensional battery models focused on stored energy, the standard versus time distance provides the most accurate physical cost estimation. However, in case of three-dimensional battery model, slice versus time distance is a good metric as its linear projections effectively filter out thermodynamic noise. So the future work could be like this optimal transport metrics can be used for like we have used for toy models. So in future we can use for more realistic problems like lithium-ion batteries and all. And furthermore, we can extend this work for quantum batteries and all. These are the few references, and thank you so much for watching my video. And if you have any question, you can ask me. And see you. Good luck.